Hello everyone. I am Nikshita, MSc Chemistry student, and it is an audio recorded lecture for visually impaired students. Physical Chemistry Unit 3rd, Chemical Dynamics. Chemical dynamics is a fundamental branch of physical chemistry that deals with the study of rates of chemical reaction and the mechanism by which they occur. Chemical kinetics is also a branch of physical chemistry that deals with the study of rate of chemical reaction and the factors affecting these rates such as temperature, concentration and the catalyst. Chemical dynamics study of reaction mechanism and the molecular processes during reactions. Rate law Rate law is a mathematical expression that relates the rate of chemical reaction to the concentration of the reactants each raised to the power which represent their order in the reaction. Rate is equal to K a to the power m or b to the power n, and r is the rate of reaction and k is the rate constant, and uh, a and b are the molar concentration of the reactants, and m and n are the order of reaction. Complex reaction. A complex reaction is a chemical reaction that takes place in two or more elementary steps, involving the formation of one or more intermediate species before the final product are obtained. Kinetics of a parallel reaction. A parallel reaction is a type of complex reaction in which a single reactant undergo two or more different reactions pathway simultaneously leading to the formation of two or more different products. One product is main product and other are the side product. Hence it is also called a side reaction. But every reaction have its different rate constant and different activation energy. Firstly, A changes into B and having rate constant K1, and A changes into C having rate constant K2. A, B, C. Initial when time t is equal to 0, the initial concentration is A naught, and B having concentration 0 and C having concentration 0. At final concentration, when the time t is equal to 0, A having concentration A and B having concentration B and C having concentration C. Above parallel reaction may be written as minus dA by me dt is equal to dB by me dt is equal to K1 A की concentration. A changes into B having rate constant K1. Minus dA by me dt is equal to dC by me dt is equal to K2 by me K2 into A की concentration. A changes into C having rate constant K2. Concentration of A after the time T may be obtained by the taking of rate law equation corresponding to the A. Minus dA by me dt is equal to K1 plus K2 multiply the concentration of A. So integration of minus dA concentration by me dt is equal to minus K1 plus K2 the integration of dt 0 to t, and ln A naught concentration by me A concentration is equal to the minus K1 plus K2 multiply time t. So the concentration of A is equal to the A naught E to the power minus K1 plus K2 into T. So the concentration of A is equal to the A naught E to the power minus KT, where the K is equal to the K1 plus K2. Concentration of B after time t must be calculated by taking rate law corresponding to the B. dB by me dt is equal to the K multiply the concentration of A is equal to the K1 A naught e raised to the power minus K1 plus K2 multiply time t. dB by me dt is equal to the K1 A naught e to the power minus k1 plus k2 multiply time t. dB is equal to k1 a naught concentration e to the power minus k1 plus k2 into t and dt. So the integration of dB from 0 to b is equal to k1 a naught a naught concentration and integration of e to the power minus k1 plus k2 dt from up lower limit 0 and having upper limit t, and b is equal to k1 a naught concentration e naught to the power minus k1 plus k2 divided by minus k1 plus k2 having limit 0 to t is equal to minus k1 a naught concentration divided by k1 plus k2 and e raised to the power minus k1 plus k2 into t minus e raised to the power minus k1 plus k2 multiplied 0. So the concentration is equal to minus K1 A naught concentration divided by K1 plus K2, then e raised to the power minus K1 plus K2 the power t minus 1 is equal to K1 A naught concentration divided by K1 plus K2, then E1 minus e to the power minus K1 plus K2 the time t multiply time t. So the concentration of B is equal to K1 divided by K1 plus K2 multiply by A naught concentration minus A naught concentration e to the power minus K1 plus K2 into time t. So the B is equal to K1 by divided by K1 plus K2, the initial amount of A minus the amount of A after time t. Concentration of C after time t may be calculated by taking rate law corresponding to the concentration C. dC by my dTe is equal to K 8 concentration. dC by my dt is equal to A naught concentration e to the power minus K1 plus K2 into T is equal to K2 A naught concentration e raised to the power minus 1 K1 plus K2 into T and dt. dc integration putting power 0 to c then is equal to k2 a naught concentration and integration of e minus k1 e to the power minus k1 plus k2 into t into dt raised 0 to t. Concentration of C is equal to K2 A naught concentration E naught की power K1 plus K2 divided by minus K1 plus K2 putting the value 0 to T. The concentration of C is equal to minus K2 A naught concentration divided by K1 plus K2 is equal to E naught the power minus K1 plus K2 T minus E naught the power K1 plus K2 into 0. C is equal to minus K2 A naught concentration divided by K1 plus K2 e raised to the power K1 plus K2 into T minus 1. The concentration of C is equal to minus K2 in A की concentration divided by K1 plus K2 1 minus e to the power minus K1 plus K2 into time t. The concentration of C is equal to K2 divided by K1 plus K2 A naught concentration minus A naught concentration multiply E raised to the power minus K1 plus K2 into time t. So the concentration of C is equal to K2 divided by K1 plus K2 the initial amount of A minus amount of A after the time t. Ratio of B and C. B by may C is equal to K1 by may K2. Note A is equal to A naught e to the power minus K1 plus K2 into time t. B is equal to K1 by K1 plus K2 bracket A concentration minus A naught concentration e to the power minus K1 plus K2 into T, and concentration of C is equal to K2 divided by K1 plus K2 A naught concentration minus A naught concentration multiply E raised to the power minus K1 plus K2 into T. Example: hydrolysis of a tributyl chloride. Tributyl chloride can react with water to form tertiary butyl alcohol or with ethanol to form a tertiary butyl ethyl ether. Both reactions occur simultaneously, competing for the same reactant. CH3 keep 3 CCl plus H2O, rate constant K1 CH3 COH plus HCl, CH3 3 plus CCl plus C2H5OH having rate constant K2 CH3 CO C2H5 plus HCl. Nitration of phenol. When phenol react with nitric acid, it forms a orthonitrophenol and paranitrophenol at the same time. Both products are formed simultaneously in parallel reaction, and the ortho product is main product and the para product is side product. Kinetics of the consecutive reaction or a sequential reaction: the reaction in which the reactant are converted into the product through one or more intermediate state is called a consecutive reaction. Every step has its own reactant and rate constant, and the concentration of A decreases regularly with the time concentration of B passing through the max and the finally decreased to its lowest value. The value of maximum concentration of B depends on the rate of its formation and the rate of its disappearance. Final product C will be starts after the formation of certain amount of intermediate. Therefore, the final product will form with a certain induction period. A changes into B having rate constant K1 and B changes into C having rate constant K2. The first order consecutive reaction. Initial concentration: when the time is 0, A having concentration A naught and B having concentration 0 and C having concentration 0. Concentration at time t is equal to T, the A having concentration A and B having concentration B and C having concentration C. So the A naught is equal to A plus B plus C. Concentration of A after the time t may be obtained as minus dA by me dt is equal to the K1 A and dA integration of A naught to A is equal to the integration of K dt from 0 to T. So the A concentration is equal to A naught e to the power minus K1 T. To determine the concentration of a B at any time t, we write the rate of the formation of B. A changes into B having rate constant K1 and B changes into C having rate constant K2. Minus dA by me dt is equal to minus dB by me dt is equal to K1 A concentration. dB by me dt is equal to K1 A minus K2 B. dB by me dt is equal to K1 A naught e to the power minus K1 T minus K2 B. dB by me dt plus K2B is equal to A1 A naught concentration e to the power minus KT. Multiply both sides by e to the power K2T. e to the power k2t dB by med dt plus k2b is equal to k1 a naught e to the power minus k1t e to multiply by e to the power k2t d by में dt b e to the power k2t is equal to k1 a naught in e to the power minus k1 minus k2 multiply time t and dt. uh, Integration of db e to the power k2t from 0 to b is equal to k1 a naught integration of e to the power minus k1 minus k2 multiply time t dt from 0 to time t. If b is equal to 0 and t is equal to 0, the b e naught to the power k2t is equal to k1 a naught and e to the power minus k1 plus minus k2 into t divided by minus k1 minus k2 from 0 to t. Concentration of b e to the power k2t is equal to k1 a naught e to the power minus k1 minus k2 multiply time t divided by k2 minus k1 plus 1 by k1 minus k2. So the concentration of b is equal to k1 divided by k2 minus k1 a naught e to the power minus ki k1t and e to the power k2t divided by e to the power minus k2t is minus 1 by e to the power k2t. So the concentration of B is equal to K1 by K2 minus K1 A naught and e to the power minus K1t minus e to the power minus K2t. Put the values of above equation. We get A naught concentration is equal to the A naught e to the power minus K1t plus K1 by divided by K2 minus K1 multiply by A naught and multiply by e to the power minus K1 t minus e to the power minus K2 t. A naught is equal to the A naught divided by K2 minus K1 multiply by 1 minus 1 by K2 minus K1 multiply by K2 e to the power minus K1 t minus K1 e to the power minus K2t. Maximum concentration of B is equal to the K1 divided by K2 minus K1 A naught concentration and e to the power minus K1t minus e to the power minus K2t. So the B max is equal to dB by med dt is equal to 0. So the dB by med dt is equal to K1 divided by K2 minus K1 multiply by A naught multiply by minus K1 e to the power minus K1t plus K2 e to the power minus K2t, which is equal to minus k1 e to the power minus k1 t max plus k2 e to the power minus k2 t max is equal to 0. K2 e to the power k minus k2 t max is equal to k1 e to the power minus k1 t max. K2 by में k1 is equal to the e to the power minus 1 by minus kt t max divided by e to the power minus k2 t max. K1 by में k2 is equal to e to the power minus k2 plus k1 t max. K1 minus k2 t max is equal to ln k1 by में k2. T max is equal to 1 by k1 minus k2 ln k1 divided by k2. From equation above, concentration of B is equal to K1 divided by K2 minus K1 A naught multiply by e to the power minus KT max minus K1 divided by K2 multiply by e to the power minus K1 T max is equal to K1 divided by K2 minus K1 multiply by A naught concentration multiply by e to the power minus K1 T max multiply by 1 minus K1 by may K2. So the B concentration is equal to K1 divided by K2 minus K1 multiply by A naught concentration multiply by e to the power minus Kt T max multiply by K2 minus K1 by may K2. So the B max is equal to K1 by may K2 multiply by A naught concentration multiply by E ln e to the power ln K2 by may K1 and K multiply by K1 divided by K1 minus K2 is equal to K1 by may K2 A naught concentration K2 by may multiply by may K2 by may K1 to the power K1 divided by K1 minus K2. So the B max is equal to the A naught multiply by K2 by may K1 and e to the power K2 minus K1 minus K2. And the two important conclusion from above equation. The two important conclusions which form the basis of derivation, the differential rate laws of complex reaction can be derived. These are that is the slowest elementary process is the rate determining step of the reaction and the steady state approximation which can be assumed to hold good for the reaction intermediate. We derive these conclusions as follows. Rate determining step. Suppose that the consecutive reaction A changes into B K1 having rate constant K1 and slow reaction and B changes into C having rate constant K2 and fast reaction. The reaction constant K2 is much larger than that of the K1. In other words, the reaction K changes into B is much slower than that of the B changes into C. Qualitatively, we can say that the B is formed from A to intermediate transfer to the C, and thus the rate of formation of the product C depends wholly on the rate of at which the intermediate B is formed from the A, and the same conclusion can be derived from the equation we have. K is much greater than the K1 and e to the power minus K1 T is much greater than the e to the power minus K2 T. The concentration of C is equal to the A naught multiplied by 1 minus 1 by K2 minus K1 multiplied by K2 e to the power minus KT multiply T minus K1 e to the power minus K2T. Since K2 is much smaller than the K1, the e to the power minus K2t will be must be smaller than the e to the power minus K1t. Hence, the K1 e to the power minus K2t may be ignored as compared to the K2 e to the power minus K1t. Hence, the equation C concentration of C is equal to A naught multiplied by 1 minus K2 divided by K2 minus K1 multiplied by e to the power K1t. Since K1 is much smaller than the K2, we may also ignore K1 in comparison to the K1, K2, and thus the above equation becomes which is identical equation. Thus we have concluded that the reaction with the smaller reaction rate constant is the rate determining step, and the same conclusion will be obtained if we consider the first step that is much faster than the second step and K1 is greater than the K2. In case we will ignore the K2 as compared to the K1 and K2 e to the power minus KTT in compared to the K1 e to the power minus K2t. Hence, the equation in the present case will be simplified to the concentration of C is equal to A to the A naught multiply 1 minus e to the power minus K2t. Hence, let A changes into C, B changes into C with the B naught is equal to A naught as the transformation of A to B very fast. Steady state approximation. A changes into B and B changes into C, having rate constant K1 and K2 respectively. Uh, K2 is much smaller than the K1. The concentration of A decreases slowly as the reaction rate constant K1 has small value. The concentration of B partially remains constant for a reasonable length of time during the reaction. Expect at the every bringing and at the end the this consistency results from the fact that the intermediate B is very reactive as its transformation to the C occur at a very fast rate. In fact, the concentration of B at any instant will much smaller than that of A, and this follows from where ongoing K1 in comparison to the K2 and exponential minus K2t in comparison to the exponential minus K1t. So the concentration of B is equal to the A naught multiply K by K1 by K2 e to the power minus K1t. B concentration is equal to K1 by K2 multiply A naught multiply e to the power minus K2 K1t. And dB by me dt is equal to 0. dB by me dt is equal to K1 multiply in A minus K2 multiply by me B is equal to 0. So the concentration of B is equal to A1 K1 divided by K2 into A concentration. Hence B is small. dc by me dt is equal to K2b is equal to K2 minus K1 divided by K1 multiply A. dc by me dt is equal to K1A. Influence or effect of dielectric medium of the solvent. Ionic reaction, double sphere model. Dielectric constant epsilon and charge of ion A and B is a ZAE and ZBE respectively, where ZA and ZB are the charge number and the E is the electron is the elementary charge. Initially, the ions are in an distance apart, and this particular model, known as a double sphere model, the ions are considered to remain interact as they approaches one another and form an activation complex in which the centers of the ion are separated by the distance dab. When the ions separated by a distance x, the force acting between them is, according to the Coulomb's law, force is equal to ZAZBE square divided by 4 pi epsilon naught E epsilon x square, where epsilon is dielectric constant and epsilon naught is the permittivity of the vacuum. The work done on the system is moving them together is distance dx is equal to dw is equal to minus dx. dw is equal to minus za multiply zb multiply e square dx divided by 4 pi epsilon naught epsilon x square. Integration of dw is equal to negative integration of ZAZB e square dx divided by 4 pi epsilon naught epsilon x square from infinity to the dab is equal to work done is equal to ZAZB e square divided by 4 pi epsilon naught epsilon dab. This work W is the electrostatic contribution is to the gives free energy of activation. When two ions forms an activation complex, multiplication by the Avogadro constant. L give the molar quantity. And delta G and G is equal G naught is equal to NaZA square 4 divided by 4 pi epsilon naught epsilon dab. Work done is equal to positive when the ions are of positive and negative, and dw is equal to negative when the ions are of positive and a negative. Delta G naught star is equal to delta G naught ness and non-electrolyte and a delta G naught of a electrolyte, and K is equal to KBT e to the power minus ea divided by rt and divided whole divided by h. From the equation, put the value of delta star G known electrolyte value is the delta star G naught is equal to delta star G electrical plus Na ZB E square divided by 4 pi epsilon naught epsilon DAB. From the equation K is equal to KBT e to the power minus EA divided by RT and whole divided by N. Ln K is equal to ln K multiplied by KBT and e to the power delta star G electrolyte divided by RT e to the power minus NaZA E square divided by 4 pi epsilon naught epsilon DAB RT. Ln K is equal to ln KBT divided by RT minus delta star G naught divided by RT minus NaN ZA ZB E square 4 pi epsilon naught epsilon DB RT. Ln K is equal to ln K min K2 minus ZA ZB E square 4 pi epsilon naught DAB KBT. Pre-exponential factor. This treatment can be extended to give the interpretations of the pre-exponential factor of ionic reactions. The thermodynamic relationship between the entropy and the Gibbs free energy is delta star G naught is equal to minus del G by me del T at constant pressure. The electrostatic contribution of the Gibbs free energy is given by the above equation. The electrostatic contribution to the entropy of the activation is delta G star electrolyte is equal to NaZAZB E square divided by 4 pi epsilon naught epsilon DAB. Delta star S naught is equal to NaZAZB E square divided by 4 pi epsilon naught epsilon DAB multiply by me del keep 1 minus epsilon by divided by del T at constant pressure. Delta star S naught is equal to NaZAZB E to E square divided by 4 pi epsilon naught epsilon DAB multiply by 1 by epsilon square and dE by me dt at constant pressure. Delta star S solvent binding effect. The solvent molecules in the neighborhood of an ion are acted on by strong electrostatic force which restrict their freedom of motion, and this effect is known as solvent binding or a electrorestriction leads to the reduction in the entropy and the reduction being greater than the larger the charge. And single sphere model slightly different relationship have been obtained using a different model known as the single sphere model for the activation complex. In the single sphere model, on the other hand, the reactant ion are regarded as becoming the merged into one single sphere which has a charge equal to the algebraic sum of the charge on the ions. Let R is equal to initial charge of 0 to the final charge equal to ZE. This process is carried out by the transporting from an infinite distance small increments of the charge equal to E to old where uh, uh, wavelength is the parameter that varies from 0 to z, and charge on the sphere is the lambda e, and net charge of the assembly is 0, and x is distance is equal to infinity to the r. Df is equal to the e multiply d lambda 4 pi epsilon naught E x square. The work done for moving the increment of x to the x minus dx is dw is equal to minus f dx. dw is equal to lambda E square d lambda dx divided by 4 pi epsilon naught epsilon dx square. Work done is equal to E minus E square 4 pi epsilon naught epsilon integration of lambda d lambda from 0 to z and integration of 1 minus x dx square from 0 to r. The total work of the charging is obtained by carrying out the double integration, x being allowed to vary from the infinity to the r and lambda from 0 to the z. Work done is equal to E square 4 pi epsilon naught epsilon multiply by z square by 2 and multiply by 1 by r square, and work done is equal to the E naught multiply by a is equal to za square E square 8 pi epsilon naught epsilon Ra. This work is an electrostatic contribution to the Gibbs free energy of the ion, and the electrostatic contribution to the Gibbs free energy of the reactant ion and the activated complex are A plus B changes into the A B plus minus, and RA RB is equal to R star, and ZAE ZB is equal to ZA plus ZBE, and the Gibbs free energy is equal to of A is equal to Z square A E square 8 pi epsilon epsilon naught E RA. Gives free energy of the B is equal to ZB square E square divided by 8 pi epsilon naught epsilon RB, and G of the AB is equal to ZAB plus ZB का whole square E का square divided by 8 pi epsilon naught epsilon R, and the change in the electrostatic contribution, that is delta G in this, and delta G is equal to E square 8 pi epsilon naught epsilon multiply by ZA plus ZB का whole square divided by E star minus ZA square divided by RA minus ZB square divided by RB, and the Gibbs free total is equal to the Gibbs free of the electrolyte and the Gibbs free of non-electrical. K is equal to kBT by में h e to the power minus del z delta G is equal divided by RT and multiply by R e to the power minus e square 8 pi epsilon RT, and ZB का whole square minus ZA square minus RA minus ZB square minus RB. So the ln K is equal to the ln KBT divided by H minus delta Z non-electrical and by divided by RT minus E square 8 pi epsilon naught epsilon RT multiply by ZA plus ZB का whole square divided by R star minus ZA square minus divided by RA and minus ZB square divided by RB. So the ln K is equal to ln K naught minus E square 8 pi epsilon naught epsilon RT multiply by ZA plus ZB का whole square divided by R star minus ZA square minus divided by RA minus ZB square divided by RB. Effect of ionic strength. The rate of the second order reaction between the charged species are affected strongly by the ionic strength of the solution, and this quality becomes defined as the reacting species are the same sign as the increase in the ionic strength. Increase the rate when ion of opposite sign react, and there is a decrease in the rate which decrease the ionic strength. Bronsted suggested that the rate of reaction between the species A and B should be expressed as V is equal to K naught multiply A multiply B, and K is equal to K naught multiply RA multiply RB divided by RAB, and log R is equal to negative of AZB and e to the power 1 by 2 is equal to minus AZ I square and I की power 1 by 2. A is equal to 0.509 and log K is equal to log K naught plus log RA plus log RB minus log RAB. So the log K minus log K naught is equal to log K by में K naught. Log K by में K naught is equal to 1.02 ZAZB multiply by में 1 मोल डायमीटर की पावर -3 whole power 1 by 2. Kinetics of the chain reaction. Chain reaction are the reaction in a highly reactive species are produced as intermediate, and the reaction is carried fastly for the longer time, and these reactions are also called a Rice-Hansfield chain reaction. Let us consider the chain reaction between the H2 and Br2 to form the HBr. Step 1. Br2 changes into 2Br chain initiation. Step 2. Br2 plus H2 changes into HBr plus Br chain propagation. Step 3. H plus Br2 changes into HBr plus Br chain propagation. Step 4. H plus HBr changes into H2 plus Br chain retardation. Step 5. 2HBr changes into Br2 and having a rate constant K1, K2, K3, K4 and K5 respectively. The rate law for the HBr for the from H to Br2 in temperature 500 to the 1500 K is R is equal to dH Br by me dt is equal to K multiply Br to the power 1 by 2. By the steady state approximation, dH by me dt is equal to dBr by me dt is equal to 0. Consider the dhb by me dt and the formation step is equal to plus sign and the consuming step having negative sign. HBr formed in the second and the third step and consumed in the fourth step by the steady state approximation. So the mm, HBr by me dt is equal to KBr multiply KH2 plus K3H multiply by me Br2 and minus K4H multiply by me HBr. Similarly, dH by me dt is equal to K2Br multiply by me H2 minus K3H multiply by me Br2 minus K2H multiply by me HBr is equal to 0. dB by me dt is equal to 2K1 Br2 minus K2 Br multiply by me H2 plus K3H multiply by me Br2 plus K4 H multiply by me HBr minus K5 multiply by me Br का square is equal to 0. From the above equation, we get the Br is equal to K1 by me K5 1 by 2 and Br 1 by 2. From the equation, H is equal to K2 multiply by me Br multiply by me H2 minus divided by me K2 Br2 plus K4 HBr. Put the Br here and H concentration is equal to K2 K1 by me K5 whole raised to the power 1 by 2 multiply by me Br2 raised to the power 1 by 2 and multiply by me H2 divide by K3 Br2 plus K4 HBr is equal to K2 K1 by me K5 1 by 2 multiply by me Br2 1 by 2 H2 and divided by K3 Br2 plus K4 Br HBr. From the above equation, we get dHBr is equal to 2K2 K1 K by divided by K5 1 by 2 Br2 multiply by me H2 divided by 1 plus K4 divided by K5 multiplied by may HBr divided by Br2. From the above reaction, pseudo order is equal to 3 by 2 of order x minus exponentially observed. We also find this result using the equation 6. In initial stage, HBr is equal to 0 and dHBr by may dt is equal to 2K2 divided by K3 multiplied by K1 by may K5 raised to the power 1 by 2 multiplied by may H2 multiplied by may Br to the power 1 by 2. dHBr by my dt is equal to K dash H2 multiplied by my Br2 raised to the power 1 by 2. Photochemical reaction. The reaction which occur by the absorption of photons for the suitable energy and the photon energy lies mostly in the visible or a UV region, and the photochemical decomposition of the hydrogen halides are 2Hi in presence of H nu changes into H2 plus I2, 2HBr in presence of H nu or light changes into H2 plus Br2. Photochemical combination of hydrogen and halogen to form a hydrogen halides. H2 plus X2 changes into 2HX. Kinetics of a photochemical reaction. For hydrogen chloride reaction, H2 plus Cl2 changes into 2HCl. Photochemical rate laws. Minus dA by my dt is equal to psi I naught alpha into A naught. First, Cl2 plus H nu changes into 2Cl having rate constant K1. Secondly, second step Cl plus H2 changes into HCl plus Cl in having rate constant K2, and H plus Cl2 changes into HCl plus Cl having rate constant K3, and Cl changes into half Cl2 having rate constant K4. For the formation of HCl, R is equal to dHCl by my dt is equal to K2 Cl multiply H2 plus K3 H multiply Cl2, and for Cl dCl by my dt is equal to K1 I alpha minus K2 Cl multiply by my H2 plus K3 H multiply by my Cl2 minus K4 multiply by my Cl is equal to 0 by the steady state approximation. I alpha is the intensity of a absorbed radiation. For H dH by my dt is equal to K2 multiply by my Cl multiply by my H2 minus K3 multiply by my H multiply by my Cl2 is equal to 0. From the above equation, Ki by I alpha is equal to K4 Cl is equal to 0. So the Cl is equal to K1 I alpha divided by my K4. From H put in K2 is equal to K1 I alpha divided by K4. H2 is equal to K3 H multiplied by my Cl2. From above equation, we get the dHCl by my dt is equal to K multiply by my K1 I alpha by my K4 divided by K4 multiply by my H2 plus K3 multiply by my K1 K2 and I alpha divided by K3 K4 multiply by my H2 divided by my Cl2 and multiply by my Cl2. R is equal to K I alpha multiply by my H2, and whereas the K is equal to 2K1 K2 by my K4, and rate is directly proportional to the I alpha of the absorbed radiation, and the quantum yield for the reaction varies from 10 raised to the power 4 to the 10 raised to the power 6. Photochemical rate law. Let's the photochemical decomposition reaction. A changes into the product in presence of light H nu. If a beam of intensity I not incident on reaction cell with the width of B and the cross section area S. Number of the Einstein absorption is equal to S by I naught minus I per second. I is the intensity of the transmitted radiation, and I naught is equal to the Einstein centimeter inverse and S inverse, second inverse. Beer Lambert's law. Ln I divided by I naught is equal to 1 alpha b multiplied by me a, and I is equal to I naught e raised to the power minus alpha b multiplied by me a. Put above equation in following. We get we get S is equal I naught I alpha b into T I. Quantum yield is equal to number of moles of A decomposed per second divided by the number of Einstein absorbed per second. Enzyme catalysis. Enzyme are the proteins with a high relative molar mass of the order of 10,000s or even more, or are derived from the living organism. Each enzyme catalyzes a specific reaction. For instantaneous enzyme provides the germination barley seeds and convert the starch into the maltose sugar. Step 1. Formation of enzyme substrate complex. Enzyme plus substrate changes into enzyme substrate complex having rate constant K1 and K minus 1. And the step 2. Decomposition of the complex. Enzyme substrate complex changes into product and the enzyme in having rate constant K2, and it is found by the experimentally that the true equilibrium is not achieved in the first step because slow reaction constantly removing the intermediate reaction enzyme substrate complex in ES. And so according to the slow rate determining step, R is equal to minus ds by me dt is equal to plus dp by me dt is equal to k ES. By the steady state approximation for the DES by me dt is equal to K1 E by me E multiplied by me S is equal minus K1 K minus 1 E multiplied by me ES minus K2 multiplied by me ES is equal to 0. Here E cannot be experimentally measured. By enzyme consummation reaction, E naught is equal to E plus ES, and the E is equal to the free energy concentration, and ES is equal to the bound enzyme concentration, and E naught is the total enzyme concentration. E is equal to E naught minus ES, and put above equation. DES by me dt is equal to K1 E naught minus ES multiply by me S minus K1 K minus 1 ES minus K2 multiply ES is equal to 0. In this way we get ES is equal to K1 E naught multiply by me S divided by me K1 S plus K2 plus K minus 1. So we get the R is equal to K1 multiply by me K2 multiply by me E naught multiply by me S divided by me K minus 1 plus me K2 plus me K1 multiply by me S. The eliminate K1 by multiplying and dividing the numerator or denominator. So the Km is equal to K minus 1 plus K2 divided by K1. When all the enzyme has reacted with the substrate at high concentration, reaction maximum rate, no free energy left. So the E naught is equal to ES. And from the equation R max is equal to V max is equal to K2 E naught. And now in equation above, R is equal to V max multiplied by me S divided by me Km plus S. In case of Km is much greater than the S is, so equation becomes R is equal to V max by me Km is equal to K S first order reaction. Km is much smaller than the S. The R is equal to V max uh, is equal to constant or zero order reaction. When the S is equal to Km, R is equal to half Vmax, hence the Marshall constant is equal to the concentration of S at which the rate of formation of product is half to the maximum rate obtained at high concentration of H, and K2 turns the number over the number of enzymes and number of molecules converted in the unit time by which the molecules of the enzyme, and typical value is 10 to the 100 per second, and high values is 10 is to the power 5 to the 10 is to the power 6 per second.